Welcome to the 8th vodcast on special relativity, and in this final vodcast for special relativity we're going to be looking at muons and their lifetime and what that says to us about special relativity, just to bring up the study design and show you its relevance here. So the study design explicitly says that you need to be able to explain why muons can reach Earth, even though their half-lives would suggest that they should decay in the outer atmosphere. So basically in this lesson we're going to explain what that's about, and so you can see it's the last dot point in this topic of special relativity. I'll point out as well that the STEM word here is explain, so we can interpret from that that you shouldn't need to do calculations for this, even though I will do some calculations to support the explanation. But from your point of view, what's likely to be examinable is being able to explain the ideas of time dilation and length contraction, which can explain the observations to do with muons. So let's start talking about what all that actually means. So muons are a subatomic particle which decay with an average lifetime, a very short average lifetime of 2.2 microseconds. So I might just highlight that. That's important. We often use this symbol for the muon, mu, the Greek letter mu, so you might see that a bit. And they naturally occur in the Earth's atmosphere because of cosmic rays which interact with molecules at a height of about 14 or 15 kilometres above the Earth's surface. Now, you don't really need to understand what those interactions are that cause the muons, but it is important to know that that's what's happening, and we know that it's happening at this height because that distance is relevant for what we're going to talk about. We also know that muons travel very fast, very close to the speed of light, about 99.9% of the speed of light. So what we're going to see in this is that the we will see the application of special relativity to some practical things. So the reason VCAA have included this dot point in the study design is because perhaps up till now a lot of the things we've been talking about have been perhaps interesting and confusing, but maybe haven't seemed very practical, and a bit more like a trick or a gimmick. But this will kind of show that there is hard evidence to show that this weird theory is definitely what's going on. So let's just return to this lifetime thing, 2.2 times 10 to the negative 6 seconds, or 2.2 microseconds. We need to be specific about what we're talking about with time. So remember, when we talk about time in special relativity, we're really referring to two events occurring and the time between those two events. And so when we're saying this is the lifetime of a muon, what we're referring to is the lifetime in its frame of reference. So remember, we refer to proper time as being the time when we have two events occur in the same place. So it's the time interval between two events in a reference frame where those two events occur at the same position. So I'm just going to draw a really crap-looking muon, which will just be this sort of ball thing. And let's say that what I've just drawn there is the creation of a muon. So let's call that creation event A. So I'll make it blue to kind of indicate that. I don't want to highlight it. Let's make it blue text, which hasn't even worked. Alright, let's go with that. And then, so that occurs at some time, which I'm going to represent on the clock here with the blue line. Okay, so event A occurs at this time. Now, let's say we're in the reference frame of the muon, which means its position isn't changing. But sometime later, in particular, on average 2.2 times 10 to the negative 6 seconds later, that muon then decays, or it dies. So let's say that is event B. So I'll just do that here, event B. Sorry. That's what I tried to do the first time. Okay. And just represent that on our clock like this. And so event B occurs at some time later, but the position has not changed. And so that that change in time, that time that's passed between those two intervals, that is our proper time. So I'm just going to put in here, this refers to T0. So that's our proper time that's passed. Now what's important here is that we can do a calculation to see how far it should actually be able to travel in that time. So I'm just going to bring that calculation up, which a calculation I've prepared earlier. I didn't mean to bring it so far down, but there you go. So if we were to calculate how far it travels in this time, well, it's just a speed times time equation, so we know it's travelling at 99.9% of the speed of light, which is here, for this amount of time. So it should travel that far. So that is 6.59 times 10 to the 2 metres, that's about 660 metres. What we just said is that it's created this high, at that altitude. So just for the visual people among us to help see what we're actually talking about here, what we're saying is that we have, here's the surface of the Earth, and let's say Everest, Mount Everest, great drawing there, which is, this is about, I think, 8 or 9 kilometers high. Really good drawing there. And our muon, well, it's created up here, and it's moving down at very fast. But this is from here to here, from where it's created to the Earth. It's 15 kilometers, and it's, if we were in its reference frame, then what we're saying is that it would decay after only 660 meters, so it would decay, it would make it nowhere near, it would decay sort of here. This drawing's obviously not to scale, but you get the idea. Now the problem is that we know we can measure in a little laboratory down here. So here's a little science lab where they're conducting some experiment. Oh, that is a bad science lab. They're doing some bad science there. But they definitely detect the muon. In their sort of base camp of Mount Everest, they detect the muon, so it's definitely making it to the bottom. So how do we explain how it's possible for it to come this far? Well, hopefully you guys are starting to get the idea here. You know what's going on with special relativity a little bit. So the problem is that even though the muon says that it only lives for 2.2 times 10 to the negative 6 seconds, we on Earth say the muon's moving very fast, and therefore its clock is ticking slower, which means that in our frame of reference it's going to have a longer lifetime. And this is the essence of all you'd need to explain on an exam, but I'm just going to show you the calculations to back that up. So I've just prepared them over here. So from the Earth's point of view, let's just look at what gamma is. So gamma, our Lorentz factor, which is this. We can calculate that since we know that V is 0.99 of C. So we get a gamma factor of 22.4. Therefore, when we measure the time interval in Earth's frame, so that's this value, it's going to be 22.4 times bigger than the proper time. So we're going to get a lifetime of this. It's still a tiny lifetime, but significantly bigger, 22.4 times bigger. So let's calculate then what that means for how far it travels in Earth's frame of reference. Basically, we now do the same calculation, but the time that we're saying it will live for is this value, rather than the 2.2 microseconds, and that gives us this distance which it can travel in that lifetime, and that is 14.7 kilometres. So if we just change those units to kilometres, we get 14.7, which is, like we said, they occur about 14 to 15 kilometres above the surface of the Earth, so that is now within range to be able to detect them at the bottom. So basically we've been able to explain how it is, let's just refer to this, explain why muons reach Earth even though their half-lives would suggest that they should decay in the outer atmosphere. Now you're likely to get a question where it's going to say, you know, two students are arguing about whether muons can make it, and one student says that because they only travel at, because their lifetime is only this long and they travel at this speed, then they should only be able to travel this far, and so we won't detect them. And you would need to explain that that is using non-relativistic calculations, and you would need to explain that this speed is so fast that special relativity needs to be taken into account, and when you take that into account, time dilation occurs, which means that its lifetime, according to someone on Earth, is much longer, and so therefore it's alive long enough, or it does not decay for long enough to travel far enough to reach the Earth. So that's the sort of explanation you need to give. Now, and I think that would be sufficient, but I'd just like to add a little bit more to show you how we can go from the flip side, because I've given this explanation from Earth's point of view. But then we need to be able to say, well, what does the muon think? Because the muon will surely agree that it hits a little nerdy scientist down here. They have to agree on those things, and yet it's still saying that this is its lifetime. So how can we explain that? Well, we need to think of what the flip side of special relativity is. We've looked at time dilation. If we get in the muon's reference frame, so we're dealing with proper time, then the two events that it's measuring, which is it being essentially created and then it decaying, those two events might occur at the same time for it, the same position for it, but the positions of the Earth where it is created and where it decays, those positions are in a reference frame which is moving relative to it. In other words, it says that all of these things, the Earth and Mount Everest and all these things, they are moving upwards at 0.999 c. And because it measures them to be moving upwards at that speed, and so these 2 points where it decays are in a reference frame which is moving relative to it, then it's not measuring proper length. So what it is going to measure is a squashed version of the world. Look at that. That is handy. And so basically it says the Earth is not 14 or 15 kilometres high. I'm just going to move all of that. Ooh, that doesn't work so well. I think you get the idea there. I'm not going to bring everything down. But basically, it says this bit is wrong. It's the 15 kilometres that it disagrees with. It says, no, I'm still only alive for this amount of time. It's just that I don't need to travel, and so this is wrong as well. Just says, well, to be able to reach the nerdy scientist down here, I don't need to travel 14 to 15 kilometres. I only need to travel about 660 metres because Mount Everest is so short and the Earth's atmosphere is so short because it's all been length contracted. So they come to the same result, that result being that, yes, it reaches the Earth, but from two different points of view. So Earth says, well, the muon lives longer, that's how it manages to travel so far. And the muon says, no, I travel at this amount of time, but I don't have to travel very far. And that's the end of my vodcasts for special relativity. I hope that they've been helpful for you to be able to catch up or get ahead or be able to understand concepts at your own pace. If you've got any questions, please do comment in our classroom or on YouTube or anything like that.